Okay, so speaking of McGill, since you mentioned it, this is a talk that I just gave at McGill. They invited me to go there in the middle of January, which I think they expected that I would say, oh, I'll just do it virtually because it's too cold to go to Montreal. I think they had forgotten that I got my undergrad there, so I was so excited to go back. I said, I'm coming. So it was a 45-minute talk, so I'm going to go pretty quick on some slides, and I've removed a few. This is the the topics I will touch. Some key people for making this possible is Andrea Mollad at Goddard for the GEOS, Chris Hill at MIT for MIT GCM. But there's a long list of people that have made this simulation possible. I will mention a few as we go ahead. To start with some motivation, the reason we are interested in having high-resolution nature runs is because if you prescribe the atmosphere on an ocean to drive an ocean simulation, you're missing some key processes. And similarly, for the atmosphere, if you prescribe SST, you are missing some key interactivity. So one of the processes that we want to capture is the interaction between mesoscale eddies and atmospheric water fluxes. And this is one example of such interaction where the ocean forces the atmosphere at scale smaller than 400 kilometers. And what ends up happening is that ocean mesoscale moisten the atmosphere. They, if you run, for example, simulations where you remove the eddies, but you have the same mean fields, you would have, obviously you would not have the SST anomalies, but importantly, you also would not have turbulent heat flux anomalies that are explained by the presence of the mesoscales. So this is one of the mechanisms that explains the importance of mesoscale eddies in driving turbulent heat fluxes. And so I want to go quickly because a lot of material to cover. So the summary of one of the reasons why we're doing that, there's many, but one of them is that the traditional view that the ocean responds passively to the atmosphere forcing is being challenged by a number of studies that show that ocean mesoscale eddies force the atmosphere, but it's also the the traditional way of forcing ocean circulation models with a prescribed atmosphere kind of starts to fail and not to represent many important processes in air-sea interactions. So that's one of the motivations why we do that. So what we had available at the start is on the MIT GCM ECCO side, we had been experimenting. Can you see my screen, Dan? My screen, my mouse, when I move it? No?
Yes.
No. Okay, perfect. So we had experimented with high resolution ocean only simulations. So this figure here to the left is from a 148 degree ocean only simulation that was with prescribed atmospheric forcing. And similarly, our colleagues at Goddard had been experimenting with very high resolution atmosphere simulations that had prescribed sea surface temperature. So the idea is, let's put these two things together and let's see how the interactivity will modify the air-sea interactions in the atmospheric and oceanic PBLs. This is a big undertaking, and you could wait forever to make things perfect. We had a deadline, which really helped, and the deadline was this diamond experiment. So this is, if we were waiting to have everything perfect the way we wanted it to be, the simulation would probably not exist. We are actually still working on parts of what we wanted to have. But this deadline meant that we ran what we had available at the time. This is it was in 2020. And so what we had ready was a 4 kilometer, well, it's a 1/24th degree ocean, so 2 to 4 kilometer ocean under a 1/16th degree nominal atmospheric, a 6 kilometer atmosphere. So this is the coupled simulation that exists now. Just to give you some idea of how we've been progressing. So, and it's also happens to be the spin up. We worked on a data constraint 1/6 of a degree global ocean simulation that's on the so-called CubeSphere 510 grid. It was constrained using the adjoint method. From there, we moved to a 12th of a degree on a so-called latitude-longitude polar cap grid. And from there, we moved to a 24th of a degree. 48 is this ocean simulation that I just showed. And then this is where we start coupling with the atmosphere. And we have now in hand 14 months of simulation of this 1/16th degree atmosphere over 1/24th ocean. Where we'd like to go is we'd like to have this ocean with many improvements under a 1/32nd of a degree atmosphere. We'll see if we get there. So this is some details of the, some configuration details for the atmosphere and the ocean. I just put the slide there and it's gonna be whoever downloads it, but I don't wanna, unless there's questions, so I can come back to that. But one of the key things that makes these simulations kind of fun and interesting is we output a lot of diagnostics. So on the atmospheric side, we output hourly instantaneous of all 3D prognostic variables. And then we output some 2D 15-minute instantaneous variables, lots of hourly averaged diagnostics. So the thing is, imagine that you have that you're able to go and put an instrument almost anywhere on the globe, in the atmosphere or the ocean, and collect observations. This is what this nature run provides to you, and it becomes very useful for many process studies. So on the ocean, we went with hourly output of all prognostic variables, and then the surface exchanges with the atmosphere and of course the sea ice. So one of the, that's a lot of bits, right? So one of the ways that enables us to look and try to explore processes and ideas is a so-called hyperwall at NASA Ames. This is actually the previous version. They are right now, as we speak, Chris Hens is sitting here, is installing a version, I don't know if it's 3 or 4 or 5, where they've broken down the walls up and down, and much bigger hyperwall that's going to make this hyperwall here had just enough pixels so you could see our simulation pixel by pixel, and you could kind of zoom in and go and look at details. The next one, we're going to be kind of in the corner of this. And now the other thing, these are not just screens. It's literally a supercomputer. Each screen has a cluster behind it, so you can do all sorts of important, useful, interactive things. During COVID, there was, and also, I mean, this was something I've always asked, is that this is really cool, but you have to actually physically go there to explore it. I said, wouldn't it be nice if we were able to have some of that capability, not all of it, at home? So David Ellsworth created this hyperwall at home capability, where you at least can get some of this this capability, where you can see global fields, you can zoom in different temporal and spatial resolutions and explore the simulation from home. It's available. And so there is some links here that are going to be useful for people who are interested in this, and they download the simulation. So in terms of available visualizations for the simulation. So here is an example of an atmospheric field, and then basically they've made visualizations of almost all the atmospheric fields at many vertical levels. This one here is a total precipitable water vapor. You can see some of the nice atmospheric rivers hitting just now California, as we have had recently. And then this is similarly for the ocean. You can go and you have all these visualizations. So at least before you use model output, you can go and explore if you some of the fields that are of interest, and decide, yes, there are some processes there that are interesting, some that are not. This is surface speed, and you can see external tides near the coastlines, internal tides, and all sorts of other eddies and all sorts of other eddies. We are in the process of preparing and submitting a preliminary evaluation. This is some of the timing fields: December, January, February on the left, June, July, August on the right, the simulation on the top, the atmospheric reanalysis on the bottom. Just some sanity checks that the simulation looks a little bit like planet Earth. I mean, that's important. Obviously, it's not, but it looks. And similarly here for winds, this one was for temperature. For winds, atmospheric winds, we do the same thing in the atmosphere, where we compare the simulation on the right. This is a section in the Atlantic to World Ocean Atlas 18. Same thing, a section in the Pacific, just to say that, to first order, it looks like planet Earth, and then you can use it for certain things. It's going to be useful. Obviously, it's a simulation, and it is going to have issues. Some very quick preliminary science results. This is a comparison of the frequency wave number spectra. On the top is for wind stress, on the bottom is for surface current. On the left is from the uncoupled simulation at a similar resolution, a 24th of a degree, and on the right is the coupled simulation. In addition to giving you interactivity, you also have high frequency and high wave number atmospheric forcing, which you are not able to get with the available reanalysis. So some of this additional energy and frequency wave number space is not just the interactivity, but also the higher resolution temporal and spatial of the atmospheric forcing. Here is an example, a published study which explores some of this interactivity between the atmosphere and the ocean in terms of the science motivation that I gave at the beginning of this presentation. I don't have time to go in detail, but it's published, and I can come back if there's questions about it. Here's another ongoing study. It turns out, and this is not my area of expertise, but apparently when you have interactivity, something that is not very easy to get in prescribed, when the atmosphere or the ocean is prescribed, is the Madden-Julian oscillation crossing the maritime continent. And apparently, Yang-Kwan Lim and Danny Du are looking at these events in the coupled simulation, and the interactivity allows this more realistic crossing of the maritime continent. And so one last example is one of the things that we do with these high resolution simulations. They're great for carrying out ocean simulation, ocean simulation experiments. Sorry. So this one example here is where we use the coupled simulation and sample the surface winds and the surface currents in the same way than a hypothetical. Actually, it's a proposal that has been submitted to NASA for a winds and current mission. And just to say a few quick things about some mesoscales. This is before SWOT launched. The simulations that we were having were giving us a lot of information about the submesoscale. So this is Tom Hain here, who says that that ocean simulations had reached a level of realism that you had to start taking them as seriously as atmospheric as observations. So and people had using these simulations has started looking, for example, at things like the transition zone between the geostrophically balanced and the unbalanced motions. This is a paper by Bo Chiu. And we thought we were doing pretty good until SWOT launched and the observations came, and suddenly modeling is way behind once again from the observations. So this is in these tracks. These are actually SWOT tracks, and the colors inside the tracks, except for the little line in the middle, is actual observed sea surface height from SWOT during the one-day repeat. And around it, I have put output from this 1/24th degree simulation. They're not at the same time, obviously, but to the eye, the character of the observed and the simulated eddies appear to match. You can check that by constructing a long track wave number spectra. And the black here, the one that goes straight, that is SWOT observations. You can see that at scales, let's say smaller than 50 kilometer wavelengths, the model and the observations collapse. This blue here is what was available before SWOT in terms of global coverage of sea level. That's an Aviso product. So I sampled it the same way as SWOT, and you can see that at low wave numbers it collapses, but then SWOT captures all this more exciting processes here. There appears to be a transition to possibly internal waves and other things. I mean, this is still under discussion what it contains. People try to filter out the unbalanced motions from the SWOT observations. This is what the second set of black lines here is. And then these two lines are from the simulation. This one is from this the 1/48th of a degree. This is from the coupled simulation because it's at 1/24th degree, so you're missing a bit of the high wave number. Just to last thing that I'm going to show, there is a paper by Anibrancina, so it's a postdoc with Jorn Callies. And they wanted to study the impact of submesoscales on the stratification. And I guess going in, the idea was that as you resolve submesoscale eddies, things would keep changing. But in the simulations that Anuban ran, it did not. So I think even though you change the vertical velocities and variability, the actual stratification stopped changing once you started resolving mesoscale eddies. So it's kind of going to be an interesting story. You know, there's many interesting stories. This is one of the interesting threads that SWAT will allow us to resolve. So I don't know if how I'm doing for time, but this is a summary slide. The GEOS ECCO nature run, that exists right now. It's 6 to 7 kilometer GEOS atmosphere on top of a 2 to 4 kilometer MIT GCM configuration, integrated for 14 months. It starts with this diamond period, and then we kept going for another 12 months to have a full seasonal cycle. Lots of model output, hourly to sub-hourly, hourly for all the prognostic variables, and then also the exchange and some diagnostics. Preliminary examination of the output includes some of the comparisons with climatological fields that I showed. It looks reasonable. I mean, it's not perfect, but looks reasonable. And there's many studies already underway, 2 to 3 that have been published. And now with the successful launch of SWAT last year, we find physical oceanography once again finds itself at fascinating crossroad between theory, computational capabilities, and observations. So I'll stop here and take questions.
Hey, Dan.
Hey, Jimbo.
Yeah, can I ask a question here?
Yes.
Dimitri, we have talked about the data access issue, right? The data is, well, the volume is on the petabyte level. Not sure what is the way forward for the community to analyze this data.
Yeah, excellent question, Jimbo. So of course we have it available on the NASA data server, but that is kind of slow, right? So we have, let's see. Oh, these are the animations, but on the same server, the simulation is fully available. It is a slow process. Now, I think we're going to be doing the same thing we did with the ocean simulation. We're going to be hopefully have many different ways. So we're going to send some output to our European colleagues that they can post it. This guy, if you know him, Tom Hain, he actually he is planning to. He has a funded project to make it available in a very very accessible way. So we'll see where he gets. And then there's, yeah, I guess I'm going to talk to you, Jimbo. I think it's going to be an all of the above kind of approach and see what works. And I don't think I mean, it'd be nice to have the one solution that satisfies everyone, but I don't know if we'll get there. Maybe Tom's solution will be so cool, so good. Maybe Podak can have
yeah,
something that they can do, but you tell me.
Yeah. So
in the past, Podak has posted selected parts of the output, right?
Yeah. So you clearly have the intention to get this data set to the public, to the community as much as possible. one thing maybe we at US Clover can do is really look into the solutions, whether we can treat this as a, NASA mission type of data set, right, to put on the AWS or put on a NASA server, but public facing without verification.
So like I said, Jimbo, it is public facing without verification at the data.nasa.gov, right? The only issue there at the moment is the it's the access.
Yeah, that does not include compute, right? It can download, but not like local compute.
It's a download, correct? No
Right.
compute, correct?
Yeah.
Yeah.
Okay. Yeah. Thanks.
Hailong, go ahead.
Yeah, thank you for the very informative presentation. So apologize, I joined late if you already covered. I was curious how the atmosphere resolution was selected at 6 to 7 kilometer resolution.
So yeah, I actually did cover it, and let me go back and show. So basically, oops.
The spectrum.
What we wanted to do. So what we wanted to do is to put these two together. This is a 48th of a degree, and this is a 3 kilometer. So that they had experimented with higher resolution, but it was kind of super slow and not working. So the original goal was to put these two things together. And so that would be, in terms of here, it would be this great, oops, my God, sorry. Would be this one down here. Unfortunately, we actually tried to put them together, and it's just, you have to be clever about how you communicate with between the two models. It becomes, the bigger the two models, the more it becomes an issue. So it was impractical at that time. We haven't given up hope. We are working on hopefully making this possible, but this deadline is what decided on that resolution. So this is a comparison of
diamond case.
Atmospheric non-hydrostatic models, the so-called diamond. So whatever we reached that deadline, whatever we had ready is what we ran, and this is what we had ready at the time. So it was not a decision; it was a deadline.
Okay,
and
all right.
Thank you. Do what we could at that deadline. I know that's not a very satisfactory answer, but that is the truth.
Thanks.
All right, time for one more quick question. Gael?
Yeah, hey Dimitri. Great presentation.
Hey, salut Gael.
How are you? I'll do it in English. So great presentations. I think it's a great reminder of how state-of-the-art something like MIT GCM is, so which I like. And I was going to ask you to maybe comment on sort of the need for longer integrations of those models. And what's on my mind is people get very excited with this kind of high resolution modeling, and for good reasons. There's plenty to learn, but they sometimes overlook, and you clarified that they've only been run for a short amount of time. So it's hard to picture or to test their sort of large-scale ocean heat transport and quantities like that.
Absolutely.
So do you want to say a bit more on that, maybe?
Yes, and actually I have, this is a great question, Gael. There's so many people that come, that would like to have a 10 or a 50-year simulation of this type. Obviously, we're already pushing the limit in terms of model output and distribution, and so we'd have to get really clever. And I have some ideas what one might do, and I'll come back to that. But then there's also the tension, you know, people say, will you please run it longer? But then, you know, what we really, this is such a marginal resolution in terms of submesoscale. So this is, you know, so it's like, do we spend resources trying to run this further, or really put all our resources to aim to get to here, where we at least we're starting to resolve some of the you know, the gravest modes of mixed layer instabilities in the winter, for example. So you really are starting to talk about submesoscales. So what I want to, there's two more things I want to say about this. One way that you get to okay, wait, this one. So some of the questions that you want to answer. So the people who are asking for these longer runs, they want to do OSSIs, for example, right? They want to do observation system simulation experiments. But another reason why people want longer runs, they want equilibration. So Hjorn's approach was saying, well, let's not run this simulation globally, but let's take a basin that's big enough so that things kind of sort of equilibrate away from the boundaries. So this simulation was run in this region for 50 years, at least till equilibration of the thermocline and the so that's another way that you can get around this desire to do long simulations for process studies. You can maybe do them regionally. And finally, one thought of being able to run these kinds of simulations for a long time, but without overwhelming the you know, the disk storage, would be to save not the full fields, but to save lines through the fields. That was an idea that Chris Hill had a long time ago, maybe 10 years ago, I think, when we were getting started with that instead of saving everything, you save lines, and then you can recreate, not exactly, obviously, because of the nonlinearities, but you can recreate approximately everything from the simulation if you have the boundaries. Let's say if you save 10 by 10 degree lines. And the really cool thing that, at least in the ocean, that capability now exists. Mike Wood has written this package where you could run, because the issue is not running this thing, but it's saving the model output. That's really the big cost. Like, CPU cycles are becoming cheaper and cheaper, but disks are not kind of following at the same level. So one idea, perhaps, I mean, ideally, yeah, you want to run this for 50 years and save everything. But if that's not possible, one might think about saving along these lines and then reproducing you know, variables through these regional simulations or global. You also save pickup time, so you have capability of reproducing what you want mostly without saving everything right away. Gal, did that answer your question? But this is a great question. I mean, that's such a, you know, it's a challenge.